We're going to review closure property. Again, we talked about this a little bit in the expressions unit, so we're just going to put some formalities together. So the closure property, it is when an operation is performed on either a number set, meaning natural numbers, whole numbers, rational numbers. Okay, so it's when an operation is performed on a number set or polynomial, and the result is always in the same set. So if it's always in the same set, that set is said to be closed under that operation. Okay, so let's look at some examples. It says check the box for the following sets that are closed. So when we're trying to figure out whether a set is closed under a particular operation, really what we're trying to come up with is a non-example. All we do is have to come up with one time when it doesn't work, and that set is not closed under that operation. So our first set, 0, 1, 2, 3, 4. Okay, so we're talking about the set of whole numbers. So our whole numbers closed under addition. So if I add any two whole numbers, will I get a whole number? Yes, my result will always be a whole number. All right, how about subtracting? If I subtract any two whole numbers, will it still be a whole number? Okay, well, let's go. 4 minus 3 is 1. Yeah, that works. 2 minus 1 is 1. Yep, that works. Okay, so let's try reverse. How about 1 minus 2? 1 minus 2, negative 1. So now I have moved out of whole numbers and I have stepped into integers. So no, that will not work. All right, so that is not closed under subtraction. How about multiplication? If we multiply any two whole numbers, are we going to get a whole number? Yeah, it's just going to continue to get larger. Or if we multiply by 0, it'll stay 0. But 0 is still in our number set, so yes, closed under multiplication. Okay. Let's see. We've got smaller numbers, negative 4, negative 3, negative 2, and we stop at negative 1. Okay, so we are looking at negative integers, just the negatives. So if we add any two negatives, will we always get a negative? Yes. It's just going to become more negative. Okay. How about subtracting? Okay, so let's say negative 3 minus negative 4. What's that give me? So I'm going to keep change. So negative 3 plus 4, so I have more positives. So that is going to give me a positive 1. So this number set is also not closed under subtraction. All you have to do is come up with one example that doesn't work, and it's not closed. All right, how about multiplication? Negative 4 times negative 3, positive 12. So no, this set is also not closed under multiplication. So only addition will it stay a negative integer. All right, so here we have negative 3, all right, 0, 1, 2, 3. So here, this is the set of integers. We've got negative, 0, positives, all whole numbers, so this is a set of integers. So if I add any two integers, will I still get an integer? Well, if the positives are closed and the negatives are closed, then yep, I'm thinking we're going to stay closed. All right, how about subtraction? So negative 3 minus 1 gives me negative 4. Okay, that works. That's still in the number set. 1 minus, I love how I said 1 and wrote 0. 1 minus 3, negative 2, still in number set. So all these kind of work, because again, we're allowed to have positives or negatives. So yeah, that's going to work. How about multiplication? Well, if I multiply any two positive whole numbers, it's going to stay positive. Negatives, they'll become positive, but again, that's in our set. Negative times positive, negative, still in our set. So yeah, those are good. We have lots to choose from. All right, rational numbers. So rational numbers is just taking the set of integers, so we've got all our positives and negatives, but it's opening up to fractions. So can I add any rational numbers and still remain rational? For sure. Fractions, whole numbers, it'll work. How about subtraction? Yeah, because we're still allowed positives, negatives, all that. That'll work. What about multiplication? So, well, a fraction times 0, that's 0. Still in our number set, so that's okay. Negative times negative, positive. We can multiply any fractions. It might be a little uglier, but it'll still work. So yeah, it's all good. All right, polynomials. Now let's go back and define what a polynomial is. So polynomial, we've got numbers, we've got variables, but the key thing is that our exponents are always positive. Positive exponents on our terms. Okay, so if I add any two polynomials, so let's go back a couple days when we were adding and subtracting the functions. So that's basically adding and subtracting polynomials. So really, we're essentially just combining like terms. So yeah, we can add any two polynomials, and if there's no like terms, then we just end up with one really long expression. So yeah, we can add them. Same thing, we can subtract, because I'm going to distribute that negative like we did to all of our terms. But again, essentially it's just combining like terms at the end. So if there aren't any, you just end up with that one long expression. As long as we're starting off with positive exponents, there's no reason for that to change. All right, now how about multiplication? So I'm just going to do basic 3x squared times 4xy cubed. Okay, so if I'm multiplying, what happens when multiplying? Stuff gets bigger. So 4 times 3 is 12. X squared times x, don't forget your invisible ones, so that's x cubed, y cubed. All right, so still have positive exponents. Our expression's just going to get a little bigger. So it's closed under all of those operations. Now notice how division is not included. Okay, because division is rarely ever closed. Anytime 0 is included in your number set, are you allowed to divide by 0? No, you are not. Anytime we have a set of whole numbers, whether positive or negative, if we divide, we could potentially end up with a fraction. So rational numbers, again, rational numbers would work, except 0 is included in rational numbers. So again, you can't divide by 0. All you have to find is one time where it doesn't work. Polynomials, yeah, I don't think that would work either, because if we divide, we have the opportunity for our exponents to become negative. So that wouldn't work either. So that's why they don't even leave off division, because it's not going to be open. Now there could be a time when it is, but for all of these number sets, it's very, very rare. So let's consider the following standard. So this is one of our math standards. It says, understand that polynomials, okay, we know that word, polynomials, so poly, many, nomials, terms, so many terms, form a system analogous to integers, namely they are closed under the operations of addition, subtraction, and multiplication. Add, subtract, and multiply polynomials. Okay, there was a really wonky word in there we need to talk about. So it says, what does it mean to say that a polynomial forms a system analogous? Analogous. It's a fancy way for saying the same as. So what does it mean to say that polynomials form a system analogous, or they're the same thing as integers as related to closure? Well, let's come back. What did it tell us about integers? Integers, namely, they are closed under the operations of addition, subtraction, and multiplication. Well, up here we said polynomials, yep, they're also closed under addition, subtraction, and multiplication, just like integers. Okay, so they were both closed on everything. So choose from the following words and expressions to complete the statement below. So we're going to prove why polynomials are the same as integers, why they're both related to the closure property anyway. So choose from the following. All right, so the product meaning what are we doing? We're multiplying. So the product of 5x to the fourth minus 3x squared plus 2 and blank illustrates the closure property. So if I'm doing closure property, I've got to stay in the same set. So if I've got a polynomial, I'm going to multiply it by another polynomial. So let's look from these three and figure out which ones are polynomials. So the first expression, 4x to the negative 2 plus 6y minus 4. There should be a red flag happening right now. This is not a polynomial. Why not? That negative exponent, not allowed to happen. Okay, so then when we look at our next one, 1/27 x squared, okay, or 1 divided by 27x squared, 9y, plus 21x. What is wrong with that one? Well, 9y is good, 21x is good, but what's wrong with this 27x squared? It is in the denominator. That's not allowed because if we wrote it in the numerator, x again would be like this. It would become negative. Not okay. All right, so last one, quantity 5y squared minus 10x squared plus 15. All of my exponents are beautiful and positive. So this one is another polynomial. So the product of 5x to the fourth minus 3x squared plus 2 and the quantity 5y squared minus 10x squared plus 15 illustrates the closure property because, okay, the blank of the product are blank and the product is a polynomial. So because the integers, okay, so variables, because the variables of the product are whole numbers. No, variables are variables. Coefficient. So let's come back. What is it? The most important part of a polynomial, for something to be a polynomial, it's got to have these positive what? Exponents. So it illustrates the closure property because the exponents is key. So we're talking about exponents. So the exponents of the product are blank. So what is key about the exponents? What do they have to be? Can they be integers? No, because that includes negative numbers. Can they be coefficients? Well, are coefficients exponents? No, coefficients are the number that's in front of the variable, so we're not worried about that. Can the exponents be rational numbers? Rational is fractional. Are exponents allowed to be fractions? Not if they're a polynomial. Yes, we can have fraction exponents, it's just not classified as an exponent. Can I have exponents that are variables? No, because variable can be anything. Positive, negative, fraction, all of that. So our exponents are of the product are whole numbers. So, and the product is a polynomial. So that's just saying when we multiply, our exponents remain whole numbers. So our product is in fact always going to be a polynomial. That's what would make it satisfy the closure property. Okay, you've got some examples to do, so go ahead and try those out. See how you do.